So, ladies and gentlemen, dear colleagues, welcome. My name is Dejan Hanzalek, and you are watching the 59th talk of the scheduling seminar. Today, I would like to introduce Hugo Chareyre from Artelys company. He made his master degree at National Institute of Applied Sciences in Rennes, studying operations research, and then he spent some time in Polytechnique Montreal as a developer in operations research, working on various optimization problems. For the last 7 years, he works at Artelys company. Artelys is a software development company with 150 employees. To mention some of his projects, one of them is glass cutting, another one is scheduling project that he will present today, which uses Artelys CP solver, and he also works on Artelys nonlinear solver. He likes triathlon, which is maybe not typical for all of us, and he likes running, sometimes even making marathon. Okay, so Hugo, the floor is yours, and please go ahead.
Well, thank you for the introduction, Znek, and welcome to this presentation, where we were going to present a project that we did with Toyota about scheduling in the automotive industry. If you have any questions during the presentation, feel free to put them in the chat, and we'll take some time at the end of the presentation to answer them. Okay, so I'll start with a brief introduction of Artelys and what is the company. I won't spend too much time because it is not the topic today, but I still wanted to introduce it. Then I'll move on to the industrial context to make you understand what we are dealing with here, what is the optimization problem, and what were the results that we get at the end of the project. So, a brief introduction about Artelys. So, the company is now 24 years old. We are about more than 100 consultants. We are doing a lot of research and developments, and we are scattered around Europe. The main office is in Paris, but we have secondary offices around Europe and also in Northern America. We have some key industrial sector where we are involved. The first one being energy. So we are trying to develop the basic foundation of what we do is decision support, so decision-making tools. And so in energy, it's about answering some practical questions. It can be about prospective studies. A practical question example is what is the benefit of adding an interconnector between France and Great Britain in 2050? What will be the impact on the electricity prices? And behind this, there is some optimization problem that needs to be solved. It can be also for operational solutions. So practical question is, what's the best planning for my power plant for the next week based on electricity prices, on the grid constraints, on the weather forecasts? So again, trying to use some quantitative tools to answer some practical questions so that the good decision can be made. And we have also a key sector, industrial sector in supply chain. So this is the focus that we are making today in this presentation. So it can be just about how do I operate my supply chain network, facility location problem, how many goods should I send from one facility to another, what is the best location for my next facility, or it can be something about scheduling with the types of problems I'm going to present today. And all of these solutions are based on some key skills. So of course, operation research, optimization, but also data science. Because when we provide some decision support tool, it's a bit the same when you provide a forecast engine. It's a bit the same questions that we ask the customers than when we provide an optimization engine. In the end, it's just a decision support tool and it's something that can be involved in the decision process. So we try to gather all those skills and make it some operational softwares that run in various industries. A few words about our numerical tools. So we have 4 of them. The first one being Artelys Nitro, so which is a nonlinear solver, which is very efficient to solve nonlinear problems. So it can be also combinatorial with MINLP. And yeah, it's very nice to have this solver available at Artelys. Sometimes you can't just linearize the problem, and modeling nonlinearity is just a must-have, typically for solving some power flow equations, some pooling problems, pricing problems, this kind of models. Then we have the Fico Express optimization suites. So thanks to a partnership that we have for a long time now with Fico, we are using extensively their MIP solvers, which is the main component, their MIP solvers Express in a lot of operational environments. And yeah, it's also very nice to be able to have this component available. It's very efficient, it's very practical. Then we have Artelys Kalis, which is constraint programming solver that we developed for a long time now at Artelys. And this is the component that we used in today's project. Then we have Ampel, also thanks to a partnership with Ampel. Again, it's a modeling language this time. It's very nice also to be able to model naturally your mathematical programs. So it works very well with Nitro. So if you have a set of nonlinear constraints, it's very nice to be able to model your problem in a natural way. So each of those components are focusing on a specific types of problems. They complement each other. Sometimes we can use them in combination one with the other. And it's very nice to be able to have this palette of tools available. Sometimes we will use open source tools depending on some projects, if we have some open source constraints or some budget constraints, or if the performance are not critical. But yeah, it's very nice. Before starting, also, I wanted to give 2 examples of scheduling projects that we do at Artelys. The first one being about maintenance planning for public transit operators. So typical problem is when do I apply maintenance task on trains? So if I am a public transit operator, I have to maintain my set of subways, of trains, and I have to apply some maintenance task every 10,000 kilometers, every 20,000 kilometers. I have some min-max constraints where I have to apply some maintenance task on the trains. And in the end, I need a planning in the upcoming years to know, to make sure that I will have available trains that are working properly. So this is a scheduling project that we did at Artelys. And in the end, we are providing this solution operationally for those public transit operators. And this solution is used every day to generate some planning. It can be for different horizon, just to define a strategic planning for the next years, up to some operational planning for the next 2 weeks that can be updated every day. And here we use a combination of constraint programming and mixed integer linear programming. That's why having several available tools and is very efficient, is very nice, because you're benefiting from the different performances from each component here. Sometimes it's very difficult to find a feasible solution. You have a lot of combinatorial constraints. That's where constraint programming can be very efficient. That's where mixed integer linear programming won't be very efficient. So using a combination of it makes it an operational solution in the end. Another example is about, again, in the transport sector, about shift planning for the railway crews. So you have a set of trains, you have a set of operators, and you want to know which operator gets on which train. So it looks like a simple assignment problem, but actually it's not. you have to generate pairing trips, so back and forth trips, so that the operators are coming back out home at some point. You have a lot of operational constraints, you have a lot of work rules, of skill requirements, and it makes it a very difficult problem to tackle in the end. So that's why constraint programming, again here, a combination of constraint programming and mixed integer linear programming was used. This is something that is used again operationally. So we have some very operational constraints, making sure that the operation of the railway operators are still proceeding each day. And yeah, this is something that is used every day for our customer. Okay, that's it about Artelys. Let's focus on the project that we did with Toyota. That is the main topic today. So let's start with a bit of context. So we worked with Toyota Europe, so for the European market. And this is a sketch of what the supply chain network of Toyota is looking like. So on the left, here you have a worldwide production of the vehicles. The vehicles can be produced in Japan, in South Africa, in Europe, in Northern America, and then they are shipped to Europe, and they are received to facilities that we call hubs. And you have several hubs in Europe. And at this point, the vehicles are not fully completed yet. You still have some tasks to operate on them, and they are not ready to be shipped to the final retailer. So that's what we call post-production options. And that's the scope of the project today. It's to be able to plan those tasks on each hub. And what are those post-production options? It's typically installing a navigation system on the vehicle, installing an audio system, a tow bar, making some inspections, some quality checks, so that in the end the vehicle is fully ready and it can be shipped to the final retailer and then to the final customer who ordered the vehicle. So the scope of the project is on planning of one hub here. So if we zoom on one hub, we still have this worldwide production on the left here, where the vehicles are shipped through different means of transportation, and then they are parked in an input parking lot. And then you have these workstations, the shops, where the vehicle are going to get processed, and we are going to perform those tasks on each vehicle. And you will typically have from 5 to 20 tasks to perform on a vehicle. And once the vehicle is finally completed, all the tasks are performed on it. It's completed, and then a truck can get it and send it to the final retailer. And so to give you an idea about the numbers that are involved here, on one day you will have typically 1,000 vehicles, 10,000 activities, 40 stations, and up to 3 shifts. So the day is working on 3 shifts: morning shift, afternoon shift, and night shift. And here we try to answer the questions, when and where am I applying each task on each vehicle? And of course, there is a set of operational constraints and objectives associated to those questions. Here is an image of what a shop looks like. So here you have a set of workstations. Those are particular workstations. You have some elevators on it. I think like here we are installing some tow bar on the vehicles. And yeah, that's basically what a workshop is looking like. So about the optimization problem. So this is very close to the classical RCPSP, the resource constraint project scheduling problem. But yeah, there's a bunch of operational constraints, and it's a bit more generic than this. But this is the foundation of the problem behind it. So we get those basic constraints that makes something feasible physically. You can only execute one task at a time on the station, and you can only execute one task at a time on a vehicle. So the basic constraints. Then you have some assignments to do. So that's another set of choice to make. On which station am I making this task? So potentially you have a set of different stations, and you have a two-level assignment here. You have to choose spatial assignment, so which station, and you have to choose also the shift. So potentially a station won't have the same resources between different shifts. Potentially it won't going to be the same operators, the same tools that are available on the station on a given shift. So some tasks can be performed during specific station and specific shifts. So that's the first thing, slightly different from the classical RCPSP, even if you have some extension of the RCPSP that covers this kind of additional constraints. Then you have the task duration. So the task duration is something that models different things. So first of all, what's a task? What are we planning exactly? So actually a task is already something aggregated. We are already aggregating some activities. We are taking all the activities of one vehicle on one type of station, and we are making it a task, and we want those activities to be performed contiguously with no idle time in between them, and we make it a task. So we get this base nominal duration, which is the sum of the durations of each activity. Then we'll have, we can impact these nominal durations with different things. The first thing is the operator skills. So if the planner knows that on one given station there is an operator that is new, that is learning to do how to do a task, then it can impact the duration to increase the duration of the task so that he has more time than the other stations. Again, you can also model with this a different number of operators. If you have 3 operators on one station and you have only 1 operator on another station, then the same task is going to be completed much faster if there are several operators. So you can modulate the task duration based on this. So for now, we are just saying that the task duration depends on on the assignment, on which station the task is performed. Then we have in-out times, so the times for the operator to get the vehicle from the parking lot to the workstation, and as input and as output. So at the end of the task, he has to get the vehicle to the parking lot or to the next station. Then we have 2 types of brakes. So we have hard brakes, which are non-preemptive brakes. So it's a time window in the shift, and you know that you can't intersect it. You can plan any task intersecting this time window. So you have to complete the task before the start of the break, or you have to postpone your task after the break. So this is easy to model. It's just about updating the capacity of the resources. And you know that during this time window, the resources is just not available. Then we have soft brakes. So soft brakes are slightly different. Soft brakes are, they are preemptive brakes. So you can interrupt a task at the beginning of the break, and then you can resume the task at the end of the break. And here we just say it's just about the duration of the task. We are increasing the duration of the task by the duration of the break. So here you have a small example. So at the top here, we have the task with a nominal duration. So here we say it's not the final duration because the task is intersecting a break. So we update the task duration with the duration of the break. And potentially it can be successive. So you have several breaks. So here in the second situation, the task is going to intersect 2 breaks. So you have again to add up the duration of the breaks so that the valid duration for this task is the nominal duration plus the duration of the 2 breaks. And a few remarks about this. So this is something that we just can't preprocess out at the beginning of the optimization. The breaks are specific to each station and each shift. If they were all the same everywhere, we could just remove those time steps from the optimization. This is not something we can do. We cannot deal with it with hard breaks because potentially you have a task that is lasting 3 hours, and you have your shift that starts at, for example, 10 a.m. and you have the first break at 11 a.m. and you don't want to introduce a 1 hour in the time at the beginning of the shift. So yeah, you have to take this into account, and this is an important feature. So here we say that the duration of the task must fully depend on the start time of the task. We don't want to branch on duration variables during the tree search. And even for deterministic point of view, even for modeling purposes, we want to make sure that once we know the start of the task, we can deduce fully the duration of the task. And this is what leads to this graph. So on the x-axis, you have the start of the task, and on the y-axis, you have the duration of the task. And we get this step function here to model the duration of the task. So at the beginning, if you have your task sufficiently early, it won't intersect any breaks. And if you move it on the right, then at some point it's going to start intersecting the first break. So you have to add to the duration of the task, the duration of the break. And again, if you move it on the right, you have to add also the duration of the second break, and so on. And at some point, you will have the task that starts during the break. So you don't want to add the full length of the break. You just want to add the remaining part of the break so that it's consistent. That's why we have this downward step function here, and so on up to having no intersecting break yet. So this is something that is an important feature, and you have to model it properly within a constraint programming model. That's why we have a start-based duration feature. It's a global constraint that we have in Kalis. And yeah, it's a very important feature because you have to make sure that you propagate this information efficiently, and you want to have good bounds on your start, and you want to have good bounds on your durations. And once you fix the task start, you want to make sure that you fix your duration and this propagation is efficient, and you don't spend too much time at each node of the tree search to update this information. Okay, then we have two other types of constraints. Precedence constraints, so this is classical in RCPSP. One task must be done before another. Nothing new here. Something new is that we have also sequence constraints. So for a group of tasks, you know that you want to perform them in a row. This group is not ordered, so potentially you can shuffle them, but you don't want to insert any other task in between them. So that's a bit different. That's a bit more generic than just a precedence constraint. So here you have an example. Potentially you can move, you don't have any precedence constraint between C, E, D, and B, but you can move B before the group, but not within the group. So that's a bit more generic. So again, this is easily modeled with an interval variable within a constraint programming solver, but you have to do it carefully. Something that could, if you don't do it carefully, something that could impact the tree search is that if you don't have the right amount of propagation here, you could start branching on the task A, then the task C, and then the task B. And if you do this, you will end up with likely an infeasible node branching on the task B after the task C here is a no good choice because you won't have the time to fit the task E and D in between the task C and B. So this is the kind of things you have to think about when you do the modeling part. And that's what could make this sequence constraints a bit harder than just the precedence constraints. So if you do it properly, it works nice with the tree search. And a quick remark also on the definition for the user, for the end user. A typical way to give the precedence constraints is to provide a precedence matrix or a precedence graph. Here we have to have something a bit more generic, and we don't want the user to provide himself. If you have 10,000 activities, you don't want to define for each activity which are the predecessors, which are the successors. So we have a high-level rule-based definition, so that you have an example here for the given two constraints here. So based on the set of wildcards and task properties, you can define those constraints, and in the end, you end up with at most 10 rules that applies on all the vehicles. Another hard constraint is a specific type of resource. So we have some specific workstations that are called conveyors. So it's a specific station, and the vehicle must pass through this conveyor, and the vehicle is going to get performed some task on it. And typically, those tasks will be divided in pitches. So the vehicle must pass through n pitches, and you're going to perform a task at each pitch. And each pitch takes a fixed number of seconds, so typically 100 seconds. And every 100 seconds, the vehicle is moving forward to the next pitch. And in the end, you have to sequence sequentially each pitch for one vehicle. So here you have an example on the right. So on the top, you have the vehicle Gantt chart. At the bottom, you have the pitch Gantt chart. So each color is the same task on the top and below. So you have to make sure that your tasks are tight between all the pitch of the same vehicle. Potentially, you can have idle times between for a given pitch, but not among the same vehicle. And so this is not a resource of capacity n, because you can process several vehicles at the same time in a conveyor, but you still have a bottleneck at the beginning, at the first pitch. You can't send all your vehicles through. You can't send n vehicles through the first pitch at the same time. You still have a bottleneck at the beginning of the conveyor. And again, you have to apply this in-out times. You have to apply the brakes, and you have to make sure that the vehicle is not available while it gets processed. So that's just something a bit more generic than just the classical RCPSP here. Here you have an example visualization, what a solution looks like. So on the y-axis, you have the workstation, you have the time on the x-axis. Here we have two shifts, so a morning shift between the red arrows here, a morning shift here, and an afternoon shift on the right. What we can see is that we have very different durations for tasks. We have tasks at the top here that are lasting less than a minute, and at the bottom here we have tasks that last 3 hours. So you have to take this into account. Following the green arrows here, that's the path of one example vehicle. So it starts to get processed in the morning here at 10 a.m. Then it's going to get processed in the afternoon shift to be fully completed by 4 p.m. here. One thing we can notice here is that we have tasks that are exceeding the shift end time here, the red arrows here. And one thing I didn't mention in the hard constraints is that we did not impose to the task to be completed fully before the end of the shift. That's for actually that's just a relaxed constraint. This is something that we will deal with in the optimization objectives. So let's move on to the optimization objective. What are they? So we have several of them. Here you have a list of them. The first one being we want to minimize the number of late tasks. This is for a main reason because if you have too many tasks or if you don't have enough resources to fit all the tasks within the shift, then you're just giving the information to the user, this is infeasible, and you don't provide any reason why. So if you return a solution where you just have a few tasks that are late, then it gives much more information to the final user. Then the user can take decision on this. He can take action. He can choose to postpone those tasks to the next day. He can choose to add some new resources, and it's much more helpful for him to understand what's going on. So that's why we have this first optimization objective. That is just a relaxed constraint. And that's a good property to have in an algorithm to make sure that once you call the algorithm, you're sure that you're going to return a solution, or if you don't, you have a very good reason for it. That's something that is very helpful for the users. Then we have other deadline constraints that are relaxed deadline constraints. We have also some deadline constraints for the vehicles. We have a date time where we would like those vehicles to be fully completed. This is because you have also planning for the delivery trucks at the end, and you'd like your vehicles to be ready for the departure of your trucks. So you have also a deadline that you would like to be satisfied. Then we have a workshop efficiency constraints, soft constraints, optimization objective actually. The first one being minimize the vehicle time span. So once we start the first task on a vehicle, we would like this vehicle to be completed as soon as possible. Because if you, in the day, if you start all the vehicles and you don't complete them, it's not a good planning. Actually, there are some internal management of how the workshop is organized, and you have some intermediate staging area for the vehicles that are getting processed, not fully completed. So you have to make sure that once you start a vehicle, you complete it as soon as possible. So again, it's an optimization objective, and we minimize the sum of the time span of each vehicle. Then we have also, we minimize the total shift of the duration. So this is to ensure that even if you fit all the tasks within the shifts, you want to make sure that you're as efficient as possible. Your planning is left shifted at most, and it ensures that you're load balanced among your equivalent stations. You want to make sure that your workstation are used in a balanced way. You don't want one station to do a lot of work and another station to be to have a lot of idle time. So that's one way to deal with it. Then we have also some station efficiencies of constraints. So locally on one station, if I take the sequence of tasks, I can try to have some good properties in the sequence of tasks that are following in one station. So one example of this is we try to minimize successive different family tasks. So it is believed, it's a learning effect. So it is believed if you group together the tasks that are of the same kind, the same family, then it's going to be more efficient because you are learning how to do it more in an efficient way. You are having the same tools available for the next task. So this is something that is not modeled in the task duration itself, but this is something that is just good in practice to do. So this is a good property that we want to have in the solution in the end. So here we end up with a lot of optimization objectives. So we have a big multi-objective optimization problem here, and we had to define a procedure here to deal with this. So that's why we introduced a goal programming method. So we made some workshop with the users, and we asked the users to rank each soft constraint and to say what's the most important one, and to give us an order here. So it's a basic lexicographic approach. You just define which is the most important and which is the less one. And so we end up with this order. And something we did additionally is that we introduced some tolerances. So those are the numbers that you have on the right here. We ask the users, how much are you willing to lose for a given soft constraint in order to improve the further ranked soft constraints? So how many tasks are you willing to make additionally late in order to improve your efficiency in the workshop? And we end up with those numbers here, and it makes sure that all of those soft constraints are active in the optimization. If you don't use this kind of tolerances, then only the first or the second one will be active in the optimization, because you will have just the most optimized solution. The optimal solution for the first objective will be very different from if you just end up having a gap of 0.5% from the optimal objective, and you introduce a degree of freedom to make sure that you're able to still have some good properties for the other sub-constraints. So there is some margin here, and we are not exactly on the Pareto front you will have if you just compare the two solutions numerically without these tolerances. So that's the table that we have here. In the end, what we get is that it's a procedure to define which solution is the best. You have two equivalent solutions, and you want to know which is the best. And in the end, you want only one solution. You want the best solution. And that's the procedure to define which solution is the best. So here we go through each sub-constraint. We evaluate it up to a given tolerance. And if the gap is within the tolerance, then we say, okay, it looks like equivalent, even if it's not strictly exactly equal, then we can move on to the next soft constraints, and so on, up to one soft constraint that will be higher than the tolerance, where the gap will be higher than the tolerance. And we can here conclude which solution is the best. So that was a challenge for this project, and that's a good method to apply. Okay, so let's move on about resolution and results that we get for this project. So in the end, what are the users interact with? So we are optimizing the daily scheduling plan. So every day we are receiving the data, the vehicle, the tasks, the resources data, the station, the shifts, and we are returning a first planning. We are running the optimization, and we are returning a first Gantt chart. And then the user can interact with it within a Gantt chart. He can visualize the solution, and it's not over yet. He has not made fully his decision. So he can check that everything looks good to him, and potentially can interact with the solution. So he can modify the solution. He can drag and drop some task in the Gantt chart. And then he can do two things. There are two additional modes. So the first one is a checker. So if the user decides to modify manually the solution, then he can call us back the scheduler service, so that we make sure that all the operational constraints are satisfied. And if not, we can detail what's wrong with the current solution. So that's an important tool also to be able for the user to interact with the solution. And we have another mode, which is a re-optimization mode, where potentially the user can modify the input data. It can add some new vehicles, add some resources, and he wants the current solution to be fixed There are some good properties in them, and I don't want to lose it. So I'm going to fix a subset of tasks, and I'm going to call the scheduler service back. And so the scheduler service is going to operate to generate some new solutions with a subset of the tasks that are already fixed. So that's also an important feature to make sure that in the end, the tool is not an automation tool. It's not a decision automation tool. It's a decision support tool. The user is still involved in the decision. Yeah, so basically that's it for the software side. For the optimization, so as I said earlier, we are using Artelys Kalis, which is the constraint programming solver that we develop at Artelys. For the modeling part, so we have an API to Fico Mosel, so which is the modeling language of Fico, and we have a nice API to model the task and the resources with this modeling language. So it's easy to add some new constraints, to make some evolutions, and to make sure that the solve is still efficient for it and to manage the data. How do we solve it? So we have an important challenge is that we have short running times. We have a lot of data. We have more than 10,000 activities. We can have up to 1 second time step for the task. So within 24 hours, it makes some large time series to manage. And we have to return the solution within 5 minutes at most. It's better if it's less than a minute. So here, of course, we cannot prove the optimality. We have to return a good solution quickly. And yeah, proving the optimality is something that for this kind of problem is not tractable. You cannot tackle this with this multi-objective scheme and all of this. It's not something that we can propose, and I think nobody can do this. And it's not very important here. We have to make sure to return some good solutions that are operationally used. So that's why we are mainly relying on heuristics, and that's still a constraint programming tree search, but heuristics are a key ingredient here. I put also some technologies here on the right about remote computing and cloud computing. This was also an important feature. It's not an optimization technology, but it's also an important feature to make sure that simultaneous user can call the service. You can scale up and you can do some support. If there is something that is going wrong in production, and then remotely you can see what's going on with the optimization. So those are technologies that are very useful to be able to scale up and to monitor the production usage. A few words about constraint programming and the use of constraint programming in this project. I wanted to mention that mixed integer linear programming will fail. This is something we do often when we get out of university and we just learned about mixed integer linear programming, and we are trying to apply mixed integer linear programming everywhere because that's the only thing we learned during our Master of Science or PhD. But in this particular case, it would just fail. You can have a model, for sure. You can model everything, but it wouldn't just work within the time limit, within the performances. You just have too many binary variables, too many combinatorial variables. So it will just fail, and you can have a model, but you wouldn't have any feasible solution within 5 minutes for sure with this number of tasks. So it could work on a time model of 50 tasks, but with more than 3,000 tasks, there is no way it would work. So that's why constraint programming is very useful. Interval variable are essential. It's a key component to be able to model the problem in a natural way. That's a very important feature. Another remark is that in recent presentation about in the last year, there is a lot of work in constraint programming that was about trying to automate the search, making sure that your CP solver is a model and run solver. You just do the modeling part and you send it to your CP solver. There is a lot of work that has been done in the recent years about this, trying to learn how to branch, trying to learn on what are the good choices to make early, trying to get some good bounds, some linear relaxations, everything about this. Everything is important here, but here, what I'm saying is that a customized search is still required to achieve operational performance, meaning that if you just take the model out of the box and you press run on your CP solver, any CP solver, you won't get the required operational performance that you need here. So there is still a need here for expertise on the CP solver, what global constraints to use, what propagation level is enough, where is the time spent at each node, so that you reach this operational performance. And yeah, there is no common API for CP solvers. So we could try some open source solvers, some other CP solvers, but there is no common API as there is for MILP solvers. For MILP solver, it's very easy to benchmark, it's very easy to make a generic modeler that can branch on multiple CP solvers. That's just not the case for CP solvers. There is a very broad variation of how do you implement the global constraints, what is the level of propagation for it, and yeah, so it makes it difficult and something very different from how a MILP solver is behaving. Finally, the results that we get. So currently we are producing the daily production plans for all the European hubs. So we started this project with just a first POC, and we went to the full production in Europe. And so we were moving on before the planner were doing manually the planning using some Excel sheets and Gantt charts printed on paper, and it will usually take 3 hours every day to make the planning for the next day. And so after our solution, the planner is able to generate the plans within 20 minutes, and you take more things into account. And yeah, there are some gains behind this. We don't have any numbers about efficiency. How many vehicles are we able to produce additionally compared to before? So we just don't have the numbers. We don't know. But there are other gains for doing this project. In the end, we end up with a solution that is, it makes the life easier for the planner. You can simulate things, how things are going to change in the future. I can simulate some plans and see how it affects the production. And we are doing the same way for all the facilities in Europe. So this has also some benefits. Yeah, so basically that's it for the results. I think that's it. If you have any questions, I think we can take them.
Okay, Hugo, thank you very much. Let me just check if people can directly ask. Allow participant to unmute. So now everybody should be able to unmute. And there is the first question in the chat. How important is to combine CP with MIL? And let me extend it. And how do you combine them? Is it like decomposition, master problem, sub problem, or is it like hybrid running concurrently, or if you can comment on it a little bit, because it seems to be a crucial point in your presentation also.
Yeah, on this particular project, we didn't use combination. We only use constraint programming.
Okay, but on other projects?
Yeah, for other projects for sure. The two examples I gave, there is one where we have a master problem that is a mixed integer linear programming, and it just focuses on main constraints, making sure that each train is covered. some basic constraints. And then it has a sub-problem that is going to generate, it's kind of a column generation where the sub-problem generate a new column, and it's something, finding a feasible solution is something hard. That's why we are using constraint programming. So it's a bit in the same way in the column generation where you use shortest path with resource constraints. Here we use constraint programming, and we can use interval variables up to and taking some dual information from the master problem. So it depends on the project. That's one way to deal with it. Another way to combine them is to get some bounds. So having a sum model and you make it a LP and you solve it, you get a bound, and it helps to guide your search. That's one way to combine those. Yeah, basically that's the two main way to hybridize them. Yeah.
Okay, thank you. Let's go to other questions. What programming language was used?
So for the optimization part, it's Fico Mosel. So that's the modeling language that is developed by Fico. So it's very similar to Ample or to GAMS or Hames or anything like this. And for the other parts, we have some Java technologies that manage the application, making sure that we are running parallel, making sure that we are satisfying the infrastructure requirements.
And then to let's say more economic questions, how long did the project take, and can we have an idea about the project budget?
How long? So we started with the first POC that lasted something like 1 month. And then, yeah, I'm not sure I can disclose all the information, but it's more about a year or something like this. Yeah.
Okay. Mm-hmm.
And about the budget, no, I cannot disclose any information about this.
Okay. So are there any other questions? Anybody wants to ask something? If not, I as usually have many questions. So one of them is for different speeds of operators, do you use multimode like RCPSP, or you calculate it as a variable duration of the task, as you have shown in the case of brakes, or how do you handle? In the case of brakes, it's like kind of nonlinear dependency on the start time.
Yeah.
Which means processing time becomes variable instead of constant, right? And for skilled workers and unskilled workers, what do you do?
It's the same way to deal with those two things. So it can be specific to each station and each shift, but we know that once we know the start time of the task, we can identify which shift it is. So we can identify how many operators I have on the station or which operator skill it is. And so we can deduce the duration in the end. So it's not like a multi-mode way to operate. We don't have several modes to operate. We know that once we know the start time of the task, we can compute the duration of the task.
Yes, but it's declarative programming anyway.
Yeah.
So,
yeah.
So it's like variable which is influenced by this decision of another variable, so to say. Okay.
Yeah.
So then there is another question which appeared. So you use CP to solve the sub-problems in a column generation framework. If you speak about decomposition technique, right? So
yeah.
CP and MILP, right?
Yeah. So that's always about decomposition techniques. It's very when we learn it at university, it's usually about column generation, trying to solve some big LPs, and you have some toy example where it's easy to apply. Once you are in industry, it's much harder because you have combinatorial problems, and you want to, in the end, you want something that is maintainable also. So those techniques are sometimes hard to scale, hard to maintain in the time, making sure that those algorithms are behaving sufficiently well, let's say with industrial strength, is something very hard to do. So we are tempted to do some industrial versions of these column generations. Something we'll do, for example, is to generate a bunch of columns at the beginning of the column generation to make sure that we'll be able to return a feasible solution, something that looks good at the beginning. Even if the column generation goes wrong for any reason, we will still have a fail-safe option, these kind of things. But yeah, those decompression techniques are very hard to put into productions, and sometimes explaining also why one solution was generated and not another is something hard to do with those techniques. So there is, it's not the classical column generation that is done for this particular project.
Okay, thank you. And then one question related to let's say the application side. So on slide 22, you have mentioned that you are trying to group tasks of the same family so that when the worker gets used to one task, the other task is similar so that it goes faster, right?
Yeah.
So this is one view of the problem, but I also know people that go in the opposite side that say when the operator does always the same task, then there is ergonomic risk that if you do for months the same task with the right hand, probably
for sure.
his elbow or whatever, right? So this is not something which is so much operational that you need to change every minute, but maybe after some time the workers need to change the workplace.
Yeah, that's actually that was a concern from the users, and that's actually the this soft constraints here that I didn't detailed. You can declare some complex tasks that are potentially heavyweight loading for the users, something that is not very good ergonomically. So in this part,
you have your hands above your head
exactly.
also on those, right?
So you'd like to make those tasks alternate between an easy task and a complex task, and make sure that you don't do all of them in a group because it's going to be exhausting for the operators. So this is something that we can do.
Okay. So any other question? If not, one question. Do you use a systematic way to elicit the relation between the different constituents of the objective function?
I'm not sure I'm getting the questions. I guess it's on the multi-objectives.
Yeah. Martin Grunhoff, maybe you can try to explain it.
Yeah.
Martin is coming.
Yeah, I'm not sure my video doesn't seem to work. So
but we hear you properly, don't worry.
Yeah. Okay, so my question is, so you talked about you discussing with the customer also about determining the relationships of the different constituents of the objective function.
Yeah.
And that is indeed on the multi-objective dimension of the project. We see that in a lot of contexts. Also, when you're looking at the SAP software and so on, there's all these different parts of the objectives that are used, right? And it's always difficult to really determine sort of if you want the weights of the different constituents, right? So what's the trade-off, what you need to do here? And this process is very tedious because you need to involve a lot of people. And my question is there a way to make this process efficient, right? Also go into these type of elicitation of these relationships here in a smart way such that we do not need to ask too many questions to get these weights, right?
Yeah, that's a good question. So that's for sure not an easy task. You have to spend some time with the users. You have to organize workshops, showing solutions, asking the users, what do you like about this solution? What do you don't like about this solution? So that you can manage to end up filling those blanks here and trying to define this order. And And yeah, that's a tedious task. And in the end, we end up with several configurations for this. So the users can change. We can switch between different rankings and different tolerances. We don't want the users to have a lot of buttons and a lot of sliders to change the tolerances as he wants, because it's going to impact the performances. And in the end, we can't guarantee it for all the possible configuration. But defining a set of possible configurations for those rankings can try to find the best of the worlds. Meaning, if one user wants specific configuration and another you wants another, then you can have a multiple choice. That's one way to deal with it. And about selecting this method, for us, it's the one that was making the most sense. If we try to use other multi-objectives methods, I don't know, weighted sum or something like this, this is something that wouldn't just work here, because the types, you don't have a common unit for everything, and you can't put euros or dollars behind each degradations. So it's something that is not, sometimes it's very hard to put a function, a measure for a given set of constraints. Typically, we spent a lot of time trying to define a measure for minimizing the successive different family tasks. How do you measure this on a given solution? So that's something that has to be done. It's a tedious task to have those workshops, but it has to be done at some point.
But up to my experience, CP is also relatively slow in very complex criteria minimization, right? So it's not like in MIL. Here
Yeah.
you cannot combine so many. And if you have just summing criteria, summing, for example, tardiness, for example, then it's much less performant than Cmax, which is my simple criteria.
Yeah, that's why you have to make sure that you are able to generate diverse solutions, so that in the end you end up with a portfolio of solutions that are diverse and that have good properties in different optimization objectives. So that's one way to deal with it. Also, when I was mentioning earlier the fact that we don't press the default tree search, we are tuning the solver so that we make sure that we are generating diverse solutions for all the optimization objectives. That's something that needs to be done also to make sure that you have in different situations, you end up selecting the good solution for the current configuration that you have for your optimization objectives.
Okay, thank you. Any other question? If not, let me ask the last one. On slide 25, you have mentioned the manual adaptation of Gantt chart, which is looking very appealing, but the problem is when you run again the solver, right? So if you run the solver and do adaptations, it's good. But if you want to run the solver again, either you lose your adaptations or you have to define what should be kept and what is like relaxed, right?
Yeah.
So and you have said that you are like fixing some of the choices made by the operator. But what does it mean, right? It's very complex
Yeah.
thing, right?
Yeah, that's a tough subject also. So we define some guidelines, what's possible to do, what's not possible to do. If you just change the data completely, if you, I don't know, add some new resources, adding, if you just completely change the data, then it won't work. Your current solution is just not longer valid. So we define some guidelines so that we make sure to still be able to provide new solutions. So there are a few different things you can do. So adding new vehicles on top of it, this is something simple, and you're sure that you will be able to add some new task at the end. That's simple to do. When you move a task, when the user, typically the modification that he can do, he can switch two tasks. It can have an impact on the task duration. So we are going to, with the checker mode, we are going to recompute the expected duration of the task, and it's going to show up in the UI in the end, and the user can visualize, okay, my duration has been updated, then I'm going to repair.
Yes, but you do this change, and then you want to rerun the optimization solver, and this change will be kept, like order of the task will stay the same, or you will decide whether to relax it or not? Or
you have a status on each task. Is it locked or is it free? So yeah.
And blocked means the same start time, or blocked means the same order, or
the same start time and same station.
Yeah, but then it's also difficult because you are creating like difficult situation for the solver, because this task is blocking the combinator.
Yeah, for sure.
It becomes harder. Like
yeah, if you shuffle too many tasks, if the user shuffles too many tasks and he press the reoptimization, then you will likely have idle times, a lot of idle times, kind of things. But that's, you can't have the best world here. You can have.
But there is a solution in that freezing of tasks when you do re-optimization with interactive optimization.
Yeah.
When you freeze a task, you don't have to specify the start time and completion time exactly. You have to give it some slack to play with, because otherwise you're going to, your optimization routine will have a very, very hard time.
Yeah, for sure. That's one way to deal with it, but you have to define this slack. That's an additional parameter, or you have to make it an optimization objective on top of the existing ones. So that's a difficult subject. So we prefer to deal with it with some particular situations. We don't allow, it's a basic tool. We won't do magic here. So if you have some basic tool, you are shuffling 5, 10, 20 tasks, it's going to be okay. You're going to be able to repair it by yourself, or you're going to see what's going on. If you shuffle too much things and it's fixed, then of course you will have a lot of late tasks. Your final solution will be suboptimal for sure. But yeah, we don't want to spend too much time on this feature about trying to add some slack on how much am I different from my original solution, trying to define a measure for it. That's something that would be very difficult to do in this context. But maybe at some point we could do this, but we didn't do this here.
Okay, thank you, Hugo, very much. So I would like just to read one of the comments of Manuel Pereira Lopez, and he says, very interesting real business problem. So thank you very much for your talk. I think it was very much refreshing that scheduling theory is used in practice, and it helps people, and there are companies that are making business on it. And then let me mention what will happen in 2 weeks. We will have another talk from industry by a well-known speaker, Philippe Laborie from Hexale. And it will be on November 20th. And the talk is about Hexale Optimizer for scheduling. So you know that Hexale nowadays has a very performant solver able to tackle large-scale optimization problems. So I hope that Philip will disclose many secrets and that we will see a very nice talk, okay? So if there are no more comments, let me close the session today, and hope to see you in 2 weeks, okay?
Okay.
Bye-bye.
Bye-bye.
Bye-bye, Mike.
Thank you.
Bye-bye, Hugo.
Bye-bye.
Thank you once more.